Hi everyone, this is Vinicius here from WITRA, and today I'm gonna show you how basically our code works. So I just want to give you a quick overview on our code. So this is just to remember, this is the code from WITRA and not the code from the robot from Scara. Okay, this one is a separate code. So I'll go through the code and explain the basic concepts and how it is written and the functions and so on and so forth. Okay, so basically what you can see here is like our include files, and I'll go through all these definitions. Okay, so these include files are the ones that we use, and specifically here the ones provided by Torodex for the interrupt library, as you can see here. Okay, then when we go down, we have a few defines. Just the server IP address, which is used for the Wi-Fi the TCP/IP communication. Okay, from the Torodex module to Scara, the robot. Okay, so I just have this IP address here. Then we have the port number, and this is the port through which the TCP/IP communication will be established. And this buffer size I'll show you later, but this is basically the size of the string that will be sent over TCP/IP. Going down, we have a few global variables. The first one is a Boolean variable, this top one. This is just a flag because we have a multi-threading code, okay, because we want to have a real-time application. So we have three main threads that do all the work, and this top flag says, okay, keep running until this flag is false, and I set it to false when I press enter. Okay, we have also another Boolean value. This is the offset flag, and this is just for the offset of the red values from the IMUs. I'll explain in details later also. Okay, then we go to the UART variables, the global variables for the serial communication. Okay, since we have three IMUs, we have three devices connecting to the Colibri module over a UART or serial interface. Okay, so we have 3 port handles for each one of the COM ports, COM1, COM2, and COM3, or on the Torodex naming A, B, and C. Okay. Now then we have, this is just for the serial communication. We have the 3 buffers for receiving data over UART. So we have receive buffer 2, and receive buffer 3, and all of them receive up to 23 bytes of data. This is the maximum size of the string that will come from the IMUs over serial interface. And we have this vector called angles, which will store all the data coming from these 3 IMUs, because as you know, each IMU sends yaw, pitch, and roll values. So we have 3 IMUs, each one sending 3 values, so we'll have a vector of 9 angles in time. Okay, then we have the sockets variables. Okay, and this is pretty simple, pretty straightforward. You just have to go to Torodex website, to the developer section, and read about using Ethernet with the Torodex modules. They have a very cool tutorial there, and you can see how to do that. We have human arm parameters, and remember that these are for the forward kinematics. Okay, and we are using the spherical coordinates for each section. Okay, so we have basically 3 sections on the human arm. One that goes from the shoulder to the elbow, and this is L1 here, and this is a generic measure in meters, so 25 centimeters. And we have another section which is L2, which goes from the elbow to the wrist, and the last one, L3, is the last section which goes from the wrist to the center of the hand. With that, we have all these 6 angles, which will give us information of these 3 sections in 3 different spherical coordinate frames. Okay, that will be used to calculate these px, py, and pz values, and those are the x, y, and z position of the center of the user's hand. This is all the basic concept of WITRA. We want to get the values of rotation, or in other words, the spatial orientation of each section of the human arm, and with that calculate the position of the user's hand in space. After that, we have the hysteresis loop, and this is just for removing noise. These variables are used for calculating a difference between the actual value of one of these thetas or phis and the difference between the previous value, so that if we have a very small difference which can be interpreted as noise, we just want to get the previous value. We don't want to change the actual value. Okay, so that will give us a more stable measure. Then we have a data log. Then this is very important because we want to save the movements of the user's arm. We want to report that to someone that may want to have this data, or even when we use that data to repeat what we did before. Okay, so we have 3 vectors, actually 4, no? For px, py, and pz, and these log g's for the gripper state, open or closed. Then we have the interrupt variables, and this is for getting a interrupt with the on-off button that we have connected to WITRA. That means then we don't have to keep checking for the GPIO value, low or high, every time. We just want to wait for an interrupt, and when the button is pressed, if the gripper is open, we'll close it, and vice versa. Then we have this main thread loop count. I'll explain it later. And then we go to our basic functions. So as I said before, we have 3 IMUs connected over the serial interface, the UART interface. So each IMU is connected to one COM port, and the Toradex Colibri, when used with Iris carrier board, it has by default 3 COM ports: COM1, COM2, and COM3. So we are using each one of those. The first function is called port open, and this is used to create and open the COM port COM3, okay, as you can see here. And this is the default code that goes on Toradex's website, as I said before, on the Getting Started section, from the developer section. Okay, this is only an adaptation to our situation. So if we have for COM3, we will also have the same kind of function for the other COM ports. So we have here port open 2, and this is for COM2, and port open 3, this is for COM1. Okay, so each one of these functions deals with opening and creating the COM port for each one of the IMUs that are connected to WITRA. And if you go down here, finally you have the port close, and this is only one function from everyone, because you just have to close the handle for that port, and this handle is passed as a parameter for this function. Okay, this is the main thread, and this is where all the magic happens, but I'll skip that for the moment, just because I want to show you first our main function, which goes, that's pretty big. And here we have our main function. We have the W main because we're dealing with Windows CE. In this main function, we have a few variables. Okay, and let's go. So these 3 Boolean variables, ret vol, they are flags for the UART communication. Okay, for each port handle, port 1, port 2, and port 3, the COM ports on the UART communication. We have also D words for thread IDs. We have Besides main thread, we have also two threads. The main, sorry, besides our main function, which is the kernel thread, we have also our main thread, which does all the magic, and our gripper thread, which only gets this interrupt. Going now, then we have these two handles for creating the two threads besides this one we are looking at. Okay, and then we go to the actual configuration. So first of all, we have the socket configuration. This is used for the wireless communication. Okay, this section here. We use sockets because this is a very transparent type of communication between systems. Okay, so it could have at one side a Linux system and at the other end a Windows CE system, and this would be very good for the communication. Okay, so I try to start up this socket and we use this function WSA startup. This is a WinSock function, and this is initializing the WS2 DLL. Okay, and I have just an error check in here. So basically here I create a socket, okay, for the communication. And we have the socket binding, and we assign all the properties for this socket to work with TCP/IP communication and with the specified port. Then we go to the connect function, which will try to connect this to a TCP server. So to be clear, we are creating a TCP client. Okay, so any interface, any equipment, any system that has a TCP server at the other end will be able to receive this information over TCP/IP through sockets. Then we go down to the UART configuration, as previously said. As we said before, we have 3 COM ports, so we will open these 3 COM ports. I'll call port open 2 and port open 3. We check the errors there, and then this will call the 3 functions that were defined up there in the beginning of the code. Okay, so we'll call these functions port open. Okay, then before we get into the main thread, we have this gripper configuration, and as I said before, this gripper function, it's basically a interrupt. So we are using the library provided by Torodex, okay, and we have a on-off button connect to a GPIO pin, and in this case is the SODIMM pin 133. Okay, and you can see here we set this pin as a input. You can see here the direction in. Okay, so basically when we press this pin or unpress it, we will send 0 or 1 to this GPIO pin. When we press the button, you have high or low. Okay, and we want to check this interrupt, okay, to the code, which will make the gripper open or close. Okay, then we have all the configuration here for that, and we have the comments, so I won't go in details how that works. And then we get to the final point. So here we have where our code begins to show things on the screen. So just welcome to WITRA, and then we create the 2 other threads. So remember that we have 3 threads in this code. So the kernel thread, which will be running with the main function, and then we have this main thread here and the gripper thread. So just to remember, the main thread does all the magic, and the gripper thread waits for the interrupt from the button. We create them, and then we get to this get char. Okay, This will act as similarly as a sleep function on the thread. That is, after we do all this piece of code up to here, this will act as a sleep, and we will stop this thread and begin running the other ones. And we will get back to this point when the user presses enter. Okay. So let's go to the main thread, and I'll come back to where we've stopped later. Okay. So I'll go up. This is quite a big code. Okay, so first we get to our main thread. So it will deal with the serial data, the kinematics, all the processing, and then send data over TCP/IP. Okay. First of all, I have some variables for timing. I just want to check how long it takes for the thread to run one loop. Okay, and then we have variables for string manipulation. Basically, when we get the information from the sensors, from the inertial sensors, the IMUs, we get a string of 3 values, 3 floating point values, which are separated by a space, and then we have a carriage return in the end. Okay, so for each one we will have to split this data, we have to parse the string. So I have some variables that will be used, and in the beginning of the code you could see that we have a vector called angles, which will store the yaw, pitch, and roll values for each IMU. Okay, so yaw, pitch, and roll from IMU 1, yaw, pitch, and roll from IMU 2, and the 3 other angles for IMU 3. You also saw that we have, I'll go up just for a little while, we have this offset flag. That is, when we start the code, we'll get whatever values we are reading from the IMUs and offset all of them. So we want to, no matter how the IMUs are oriented in the beginning, we just want to set everything to 0. So that will be as if the IMU is laying on a table with no rotation at all, because that will guarantee that every time we start, even though we don't have precisely the same orientation every time in the same positioning of the arm, we always have the same initial position. Okay, so we have these offset values for each one of the 9 angles we are reading. Okay, 3 angles from each of the 3 IMUs, and we want to store that to offset through all the code. Then we have the intermediate kinematic variables. As we said before, and as it is stated on the previous updates, we calculate the kinematics from the human arm to direct kinematics using spherical coordinates. That is, basically we have 3 sections that, as explained before. So one section that goes from the shoulder to the elbow, then from the elbow to the wrist, and finally from the wrist to the hand. Okay. So x1, y1, and z1 are the variables that will store the position of the elbow in relation to the shoulder. And the shoulder, as you can see here, is always our inertial frame, our 0, 0, 0 position. Then x2, y2, z2 will give the position of the wrist in relation to the elbow. Okay, and then we'll have the p, x, p, y, p, z, which will be the positioning of the hand in terms of the shoulder. Okay, I hope that will be clearer in the near future here. So then we go to the while loop. So as I said, we have this top one flag, and this will remain true as long as we don't press enter. So it can run to infinity unless we press enter, and then we'll stop the code. We can use this getTickCount function from Windows CE just to start a timer, like TikTok in MATLAB. We want to get the total execution time for one thread loop. This is not really important now, but it can give you a very correct measure of the time and how much time you spend in one loop. After that, we will read from each one of the COM parts, and this will give us 3 strings: receive buffer 1, receive buffer 2, receive buffer 3. Actually, this is a character array. Sorry, and this will be converted into a string right here down below. Okay, because a string will be much easier to deal with. Then we start handling and parsing these strings. Basically, I'll just explain the basic concept and you can go through the code by yourself. But let's take string str here. Okay, and this is the string to which the first receive buffer was converted. So we have a string of 3 angles separated by space and with a carriage return in the end. We get this string and we find the first position where a delimiter 1, which is space, is positioned. Okay, so we read from the beginning of the string until we find a space. This will be a position. Then we can use this C++ function substring to get a token, that is, to get a substring from our first string, which will be the value or all the characters from the 0 position until this position where we found the space. That is, that we can have now only the first value on that string instead of the 3 values. We will pass to a input string stream. Okay, we will use streams, and we will convert it to our first angle. So we had a character sequence, a string, and now we were converting it to a double variable. Okay, so basically what we did was to get the first string with 3 values, and we parsed on the first value. So now we have the first value of this string, and then we will do that for the other strings, and after that we will erase. We use this function erase so that we can erase the section that we've already read. Okay, so we will erase from 0 until the position of the space character plus 1. Oh, sorry, plus the plus 1 plus the delimiter length. After that, we can do the same thing for the other 2 values. So we will read the second value and store in another variable, and the third value, so on and so forth. After that, we will have the 9 values from angles 0, top here, to angles 8. Okay, and these will be the yaw, pitch, and roll values for each of the 3 IMUs. After that, we will set our offsets, and this is done only once because only when we start the code this offset flag will be true, and after we do that we will set it to false. This section is very interesting and very important because the IMU gets, for each of its values, yaw, pitch, and roll, it gets a value from negative 180 to positive 180. So this may be a little dangerous because depending on how the IMU is first oriented at the beginning of the code, it can show a value, for example yaw value, that is very close to 180, for example, and then when you start rotating it, it can jump to negative 180, and this will cause a very big problem to our system because it's a jump, a singularity. I mean, we don't want that. Okay, so we'll just set this point, if you are close to that, to the other end. Just to be clear, if you start, for example, let's read the first comment here. If you start and yaw is in the second quadrant, that is from 90 degrees to 180, it may cross the 180 and negative 180 border. So we will set that border to where we have 180 to negative 180, we set to 0, and all the problems will be solved. And where we had 0 previously, we will set to this border. Okay. After that, we offset every value. That is, every time you read from the sensors, whatever the value is, we will offset by the initial offset calculated. Okay, and then we will get to the actual direct kinematics of the human arm. All right. So we assign the theta and phase corresponding to the angles that we got from the IMUs, and here we do the hysteresis loop. Okay, just to remove the noise. And in the end, we convert from degrees to radians, as you can see here. And finally, we truncate the values to 2 decimal digits using floor function. So finally, we can use spherical coordinates to find the intermediate variables and the final variables for the direct kinematics. So first of all, we will calculate x1, y1, and z1. Okay. And this, as said before, we have the position 0, 0, 0 at the shoulder, and this never changes. This is our inertial frame. And then we have x1, y1, and z1 at the elbow. So this will be the position of the elbow in space. We can also calculate the position of the wrist in terms of the shoulder, and this will be x2, y2, and z2. So there's a good remark to do here. You have the same mathematical equations as you had for the previous values, and you just add x1, y1, z1. That is a very nice way to analyze it. Okay, and we do that for the last spherical coordinate frame, and we get px, py, and pz, and this is the position of the center of the hand in terms of the position of the shoulder, which will be always 0. Now we have to scale that to the reachable space on the robot side. Okay, and knowing our kinematic, the kinematics of the human arm, and knowing the kinematics of SCARA, we do these calculations, and this will guarantee that when we have our arm straight forward, this will be related to a straightforward position of the robot, and when we move to the sides, the robot will mimic this movement. Okay, this will guarantee that the teleoperation indeed works. And for safety, we set the PZ value of the robot to always be lower than 0, and you can understand that better if you go to our update talking about the kinematics of the robot. Finally, I said this is a pretty big thread, and finally we get all these values from each iteration and store them in a vector, one for each data log. So we will create then a data log for px, one for py, one for pz, and one for the gripper. Okay, and the gripper I will explain shortly. Okay, after we have done that, we can send this data to the actual robot, to the server of the robot. So we will get all this data and format a string. And it's very important to remark that this string has a JSON formatted kind of string. Okay, you can go on the internet and search for rapid JSON, and you will see that this is a very, very good way of formatting strings, because they have a whole library that will deal with this kind of information, and this will make sure that a whole variety of systems can interpret data coming from different operating systems and different coding languages, so on and so forth. Okay, and our robot expects a string that has a command here, which we call impedance, and this will set the control mode on the robot to a impedance control. Then it will receive a x, y, and z position. This will be the position of the end effector, and a gripper variable, which will account for the state of the gripper, whether it's closed or open. After we format the string and add it to send buffer, we will send it over TCP/IP to our server. Okay, and we always send a fixed buffer size, which now is 128 bytes. After we do all this iteration is done, and we can get the tick count again as we did in the beginning, and then we do this little math to calculate the thread execution time. So now we can purge our COM ports. Yeah, so we can clear all the receive buffers and go to sleep for 20 milliseconds. So this is only one iteration. So we keep doing that continuously until we press enter. And as I said before, we have another thread, which is a very simple one, not so big as the previous thread. And this is a gripper thread, which will run as long as top one is false. Sorry. So it will be like the previous one until we press enter, and this will only wait for a event, the interrupt event, and if I press the button, I will toggle here the state of the flag. So if the flag is true, I will close the gripper, and if it's false, I will open gripper and then sleep. With that, we are almost done, and we just have to go back to our main function, and we stopped here. So when I press enter, I go to this point again, I stop all the execution, and then I simply save all this data to data log. So I'll get all those vectors of X, Y, Z, and gripper and save to text files. After I do that, I will close my threads and wait for another enter. And when I press enter another time, I will clean up everything and finish the code execution. With that, we finish our WITRA code overview, and I hope I didn't go really fast. Just wanted to give you, as I said, an overview, not in-depth details, but feel free to contact me, and this code is available on the internet. And I hope this helps the future generations of WITRA. So thanks a lot for watching, and thanks for following us on Torodex Challenge.